So consider the old example that we used to construct the basis for the image and the kernel of a matrix A. So here we have the matrix A and with reduced row echelon form of A as given, which is the matrix B. So in order to determine the kernel of A, we notice that actually the kernel of A equals the kernel of B, since Gauss-Jordan elimination steps keep the kernel intact. So now we see that since we have two leading elements or two pivots, that actually we have three free variables. So x2, x4 and x5 can be freely chosen. So say that x2 equals r, x4 equals s and x5 equals t for some choice of parameters r, s and t. Then x belongs to the kernel of A if and only if x equals, well, the first coordinate x1, x2, x3, x4, x5, which equals r times minus 2, 1, 0, 0, 0, plus s times the vector minus 3, 0, 4, 1, 0, plus t times the vector 4, 0, minus 5, 0, 1. So actually we see that the kernel of A equals the span of these three vectors over here. So 1, 2 and 3. So actually we have found three vectors that span the kernel of A, which is a linear subspace of the R5, and the question is now whether this is a basis, whether these three vectors constitute a basis. Well, we also can see immediately by the location of the ones where the others have zeros that these vectors are linearly independent. So actually these three vectors can be taken as a basis. So the basis for K, or the kernel, is given by these three vectors. So we know that since each basis consists of the same number of elements, we know that the dimension of the kernel in this way equals the number of free variables, which is 3. It's a number of free variables. For each free variable we get a vector. So the dimension of the kernel is always equal to the number of free variables in the reduced row echelon form. Ibrahimovic.
Ja.
Goed zo. Mooi.
Ziet het duidelijk aan die tattoos en
Ja.
aan dat staartje.